So now we've learned quite a bit about light, but we don't just want to know light, we want to know what light can tell us about matter. So let's talk about matter really quick. All ordinary matter, what I mean by ordinary is the stuff that you are familiar with, that you actually interact with every day, is composed of atoms. An atom is the smallest piece that still carries the element's characteristics. The elements are the fundamental building blocks. As different elements bond in different ways, we actually get different materials. Today we know of more than 100 elements. Now, an atom is made up of three particles: protons, neutrons, and electrons. Protons are positively charged and found in the nucleus. The nucleus is the tiny ball at the very center of the atom. Neutrons are neutrally charged, meaning they have no charge, and they're also found within the nucleus. And then the electrons are negatively charged, and they surround the nucleus. And it's the attraction between positive and negative that holds the electrons to the nucleus, creating the atom. Now, each different element has a different number of protons within its nucleus. The protons is what actually determines the element. The number of protons we refer to as the atomic number. The atomic number is the number of protons and defines the element. So, as an example, we have hydrogen. All hydrogen atoms always have one proton in the nucleus and therefore have an atomic number of 1. Helium always has 2 protons in its nucleus and therefore has an atomic number of 2. Now, if a hydrogen had 2 protons, it wouldn't be hydrogen, it'd be helium. Carbon always has 6 protons in its nucleus. Okay, that's what it means to be carbon, is to have 6 protons in the nucleus. Now remember, protons aren't the only particles in the nucleus, we also have neutrons. So the total number of both protons and neutrons, all of it all together, is the atomic mass number, sometimes simply called mass number. So the total amount of protons and neutrons in the nucleus is the mass number. Now, to be a given element, you only have to have the right number of protons. You can actually have differing numbers of neutrons. These elements, these atoms, with the same number of protons are the same element, but with having different numbers of neutrons, they are different isotopes of that element. Okay, so an isotope is an element with the same atomic number, but differing atomic mass numbers. One great example of this is carbon. The most common type of carbon is carbon-12. Okay, so the 12 is the atomic mass number. Now, all carbon has an atomic number of 6. So all carbon has 6 protons in its nucleus. So carbon-12 must also have 6 neutrons, because 12 minus 6 is 6. Okay, so about 1 out of every 1,000 carbon atoms is actually carbon-13. Again, that 13 is the atomic mass number. So, it being carbon tells us that it must have 6 protons, and because it's 13 for the atomic mass number, it must have 7 neutrons. About 1 out of every million or so carbon atoms is carbon-14. Again, it must have 6 protons because it's carbon, and because the atomic mass number is 14, it must have 8 neutrons. Now, one interesting feature of electrons in atoms is how it is that they store energy. We have found that electrons are not allowed to just have whatever energy. Now, the energy they have is going to correspond to their location in the atom. So what this means is electrons are not allowed to be just wherever they want within atoms. They're only allowed to be at very special locations, which are sometimes referred to as orbitals if you've taken chemistry or physics previously. Okay, so one way of thinking about this is how far away from the nucleus the electron is. Okay, so going back to our using gravitational potential energy as an analogy, if the block or bowling ball were on the ground, it has the least amount of potential energy. But the farther away you move it from the ground, the higher the potential energy is going to be. We have a similar thing happening with the electrons. The nucleus is positively charged, the electrons are negatively charged, so they want to be together. As we move the electron farther and farther away from the nucleus, it's going to have more and more potential energy. So we sometimes refer to these different distances away from the nucleus as energy levels. The electrons are only allowed to be at specific places, at specific distances away from the nucleus, and therefore they have to have very specific energies to be in those locations. Now, electrons are able to move from one energy level to another, but to do so, they have to either gain or lose the exact right amount of energy. So, for example, let's start with an electron down here at what is sometimes called the ground state or energy level 0. This is where the electron has the least amount of energy. If we were to then try and give this electron 5 energy, it could not accept it. Okay, so if you look at these energy levels, we have 0 energy, we have 10.2, 12.1, 12.8, and so on, all the way up to 13.6 energy. So this electron, starting at 0 energy, if we try to give it 5 energy, it ends up in a location that is not allowed. So this electron cannot accept that energy. We have a similar thing happening if we try to give it 11 energy. Giving it 11 energy will put it up here. And unfortunately, the way that these things work, the energy is all or nothing. If the electron can't absorb all of the energy and end up on an energy level, then it can't accept any of it. So this electron will not accept 11 energy. If we give the electron exactly 10.2 energy, though, then it will easily jump up and end up on level number 2 at 10.2 energy. Now, when the electron loses energy, if it can lose exactly 10.2 energy, it will transition from 10.2 and fall back down to 0. But it must have given that energy off some way. And we'll talk about this more in a bit. The best way for it to do it is by giving off light. So as the electron drops from high energy to low energy, it's going to give off the energy, usually as light. Now, matter interacts with light in 4 different ways. Matter can emit, meaning give off light. Matter can absorb, meaning take in light. It can transmit, meaning allows the light to pass through. And it can reflect and scatter light. This is where the light bounces off. And now there is a slight difference between reflection and scattering. In both cases, the light is bouncing off. With reflection, the light all bounces off together so that you can actually see an image of what's going on. Think about a mirror or a still pond. Scattering, the light bounces off, but then goes every which direction. So think about light hitting a white sheet of paper. You don't see an image of the light in the paper because the light is scattered. All of the different colors of light are scattered, so the paper is white. So in this image, we actually have examples of all of these different things. For emission, we have the sun. The sun absolutely emits light, as well as a light bulb. Light bulbs emit light. For absorption, we actually have many different examples. We have the red chair, the blue shirt, and the green trees. However, previously we said that absorption is where the object takes in the light, which means their light isn't there anymore. So shouldn't these things be black? Well, what's going on is that these things are absorbing light, but only of certain colors, and the other colors are actually being scattered or reflected. So, for example, the red chair. We know that the red light is bouncing off. What that means is that the green and blue light must be absorbed. For the blue shirt, the blue is bouncing off, is scattering. So the green and the red must be absorbed. For the green tree, this means that green is scattering off, so red and blue must be absorbed. Okay, so some things are scattering certain colors and not others, and that is therefore the color that we see. Next, we talked about transmission. The great example of transmission is glass. Now, glass transmits visible light, but it actually does not transmit infrared or ultraviolet. Okay, that's not entirely true. It depends on the type of glass. Okay, but most glasses used in houses actually transmit visible and then block out infrared and ultraviolet. Okay, we've mentioned scattering already, so that's like the tree, the shirt, and the chair, although it's only of certain colors. We also have the white snow. The white snow is going to reflect or scatter, I should say, scatter all of the colors. And then our example of reflection is going to be this mirror. Now, with all of this understanding, we can now answer the age-old question, why is the sky blue? So, the reason the sky is blue all begins with the sun. Now, the sun is not blue at all. The sun is actually white, giving off all of the different colors of light. All of that light then hits the Earth's atmosphere. The Earth's atmosphere is the layer of air, the gas layer on the Earth. Well, because of the size of the particles that make up the Earth's atmosphere, shorter wavelengths scatter much better than longer wavelengths do. So what this means is all of the light hits the atmosphere, and the short wavelength blue light gets scattered toward us, whereas the long wavelength reds and oranges pretty much keep going in a straight line. So as we look up, when the sun is high up in the sky, no matter where we look along the sky, some of the sun's blue light has hit the atmosphere and has been scattered towards us, so we see the sky is blue. Now, this same explanation will help us understand why sunsets are red. As we look towards the sun, notice I did not say look at the sun. Don't stare at the sun, it's a bad idea. But as you look towards the sun during sunset, you notice that it is reddish. The reason for this is because we're now looking through a whole lot of atmosphere. That blue light gets scattered out very, very quickly as it first hits the atmosphere. But the reds and oranges keep going all the way to us, so that as we look towards the sun, it is reddish and orangish during sunset. Now, something that's kind of fun. So on the Earth, the sky is blue during the day and we get reddish-orangish sunsets. On Mars, depending on conditions, if there's been a dust storm, it's kicked up a lot of dust into the air, which actually causes the sky to turn pinkish in color. Okay, so during the day, the sky is pink. Now, if we have a pink sky on Mars during the day, what color is the sunset going to be? It's going to be blue. The long wavelengths in that case are getting scattered better than the short wavelengths, and therefore the short wavelengths will come through during a sunset, and the sunset will be blue. We actually have images of blue sunsets on Mars. All right, here's our second clicker question. Why is the sky blue? A, it is a reflection of the blue oceans in the sky. B, the atmosphere emits blue light. C, blue light is more easily scattered. Or D, the atmosphere absorbs red light. Go ahead and think about it and we'll discuss in just a bit. So why is the sky blue? The answer is C. Blue light is more easily scattered by the particles that make up our atmosphere, but it could be possible to have different colors of sky on different planets.